functionality that the tank inherited. Now we want the distance between 2 points in space. One is the tower location, and drag it right here inside the if statement. So if the tank is valid, then we can access its location with getActorLocation. Excellent. Since we're working in this if statement, I'm going to move these other comments here inside of it, because we know we can't check to see if the tank is in range if the tank isn't even valid. So I'd like to challenge you to rotate the turret towards the tank. Now we only want to do this if the tank is in range. We have the distance, so now we need a fire range variable. So create a float called fire range in the tower class and expose this with uProperty. We'd like to be able to edit this from the editor. Now you're going to check to see if the tank is in range. If it is, call rotate turret. And rotate turret needs a look at target. You're going to pass in the tank's location. So pause the video and implement this behavior now. Call this fire range property. So on the default blueprint. Now, if you made yours edit anywhere or maybe edit instance only, that's totally fine. It's really a matter of preference, and we can change it later. I'm going to give it a category as well, and I'm going to call this category combat. Let's go into tower.cpp, and we have this next point here, check to see if the tank is in range, which means we need to check to see if distance is less than or equal to fire range. We have less than or equal to, and not just equal to, because from frame to frame, the distance may actually be greater than fire range one frame and less than fire range the next frame, completely passing fire range, so it may actually never become exactly equal to fire range. In fact, with floating point values, two floats being exactly equal is quite rare. So we have this if check, and if we get to the inside of it, that means distance is less than or equal to fire range. The tank is now in range, which means this comment can be moved right there. Now, if in range, rotate the turret toward the tank. That means we're going to call the rotate turret function. That's our protected function that we put in base pawn. Now, rotate turret takes a look at target, and we need the location of the tank. So that's going to be if the tank pawns and find BP pawn turret and open full blueprint editor. Now, up at the top right, we see parent class base pawn. Range, so we don't see any movement from the towers. But if I get in range, look at that. Now they're following me around, and it looks quite threatening. Now, 300 units is not that far away, so what I'd like to do is edit that distance. So from here in BP pawn turret, I'm going to select BP pawn turret self, and here's the combat section. I'm going to go ahead and set this to about 700. Now if I hit play, I'll see that they won't be rotating while I'm moving back here, but as soon as I get in range, now they're looking at me. Perfect. So in summary, we have created the tower class. We now have an enemy for the tank. We also rotated. So we're going to create a fire function, and we're going to associate this function with our left mouse button. And here you can see that I'm drawing debug spheres at the tip of our turret barrel just to prove that this action mapping is working. Whenever I click the left mouse button, something is happening. Hey, welcome back. In this video, we're going to talk about creating a fire function, or a function we can use for when we want to spawn our projectiles. So we're going to create a fire function, and we're going to bind it to an action mapping. Now, we've been using axis mappings. An action mapping is similar. Let's talk about it. Now, here's a section of a screenshot of the fire action mapping that we have in our project settings. You'll see that we have the left mouse button assigned to the fire action mapping. Now, an action mapping is very much like an axis mapping. You can assign a key or a button to it, and just like an axis mapping, it requires a function button to it. Action mappings are slightly different. A callback function bound to an action mapping takes no input parameters, and all that happens is when you press the button, the function gets called. What goes on inside of the function is up to us as the developer. Now, action mappings are one-offs. They don't happen every frame. They only happen once when you press the button. So if you release the button and press it again, the function will be called once more. Now, when we bound functions to the axis mappings, we used bind axis. For action mappings, we use a function called bind action, and it takes inputs similar to bind axis. It takes the name of the action mapping as a string literal. It also requires a pointer. Not require. There are two options for this input parameter, the enum con and now I'm here in base inherit this function, just like rotate turret. So under rotate turret, I'm going to create a void function called fire that takes no inputs, and we can go ahead and define the fire function in basepawn.cpp. So here's basepawn.cpp, and just under rotate turret, I'm going to place the fire function, and we need to fully qualify this function name and give it a function body. So now we have a fire function. Now the next step is to bind this to an action mapping. Now we only want to bind this function in the tank class because the tank is the only class that will be taking user input. We'll be calling the fire function in the tower class later, but that will be as a result of code we create and not as a result of user input. So we're here in tank.cpp, and we're going to bind this in setup player input component just like we used bind axis. So we're going to use the player input component. So player input component, and the function is going to be bind fire, the fire action. So go ahead and fill in the parameters with values that you think are appropriate. Use the location of the projectile spawn point. Now, the projectile spawn point is a useScene component, and useScene components have a function called getComponentLocation. This returns an F vector. This is what you can use to get the projectile spawn point location. Now, when you call draw while, I'm back here in base pawn, and so we have spawn draw debug location. So that will be what I pass in as the second parameter. And next we need I'm just going to have our lines hang around for 3 seconds so we can make this false because we don't want them to persist forever. We're going to give this and I'm going to that of the function, and we bound. We're almost ready. So if I get close to our towers, I can see that they are drawing debug spheres, proving that they're calling the fire function, and they're doing so every 2 seconds. Now, in addition to that, they're only calling this function if I'm in fire range. If I get back here, you'll notice that they're not. We're using that in the tank class because we've bounded class. So since we'd like the fire function called every so often on the tower class, we need to talk about timers. Now, Unreal Engine has the ability to set timers using a class called FTimerManager. There exists a World Timer Manager which manages timers in the world. Now, this World Timer Manager has a function called setTimer, and setTimer takes a number of inputs, such as a timer handle. This is a handle to a specific timer managed by the timer manager. This allows the manager to have multiple timers, and we can access the timer info for each one by using the timer handle as a sort of name or ID for that timer. This is an object of type FTimerHandle. So we create a timer handle and pass this in to the setTimer function. Now, setTimer also requires other inputs, such as the rate or the amount of time that we should wait before actually doing something. Now, that something is going to be in our callback function. We create a function and we bind this function to the timer so that as soon as enough time has elapsed, specifically the timer rate, then our callback function can be called. So we've seen that we need a few things for our timer, and we're going to place these things in the tower class. So let's go into tower.h, and here in the tower.h file, we're going to add some private variables. So just under fire range, we're going to need our timer handle. So this is an FTimer handle, and we can simply call this fire rate timer handle. And we also need a fire rate. That's going to be a float. We're going to call this fire rate, and we can initialize this to 2.f, so that way we'll have a 2-second wait before our callback function actually gets called. And speaking of callback functions, we actually need one. So we're going to make a void function, and we can call this check fire condition. So we have a timer handle, and as soon as we set the timer and it starts running, then we have 2 seconds to wait before the timer actually results in our function being called. And I'm calling this check fire condition because we can check to see if our tower should be able to call the fire function. So we can place some conditions that we can check to make sure that fire should be called. Now, we have the fire condition function declared. We need to define it. So we can go into tower.cpp and define the function here. I'm going to place it under begin play. So I'll give it a function body and the aTower class name just before the function name. So now we have a function, but we actually need to set the timer so that that time will start running and the function will be called at the end of that time. And we can set the timer here in begin play so that it starts running from the beginning of the game. So we mentioned the World Timer Manager, and we can access that with a function called getWorldTimerManager. Now, getWorldTimerManager returns an FTimerManager object, and since we're using that type, we're going to need to include the header file for FTimerManager. So here is the include. It's simply timermanager.h. And we can also see some of the functions that belong to this class. So scroll through these if you're interested in all of the different functions that belong to FTimer Manager. So we can include this header file up here at the top of Tower, just under the other includes. So now that we have that header file included, now we have access to the World Timer Manager, and the function that we're interested in is called set timer. Now, Get World Timer Manager simply returns an FTimer Manager. It doesn't return a pointer, so we're going to use the dot instead of the arrow, and we're going to call set timer. Now, set timer has several versions or function overloads. Now, VS Code has this pop-up that lets us go through each overload and see the different versions of this function. And the version I'm interested in first takes an FTimer handle, and we're going to use our fire rate timer handle, which we declared in tower.h. Now, the next parameter for our particular function overload is going to be the user class. Just like in bind access and bind action, this is the class that we're working in, which we're binding the function for. That's going to be this. Now, next is going to be the callback function. That's going to be our A tower check fire condition, that function that we just created. Now, we do need the address of operator because set timer takes the function address. Now, the next parameter is a float for the rate. This is going to be how much time should pass before our callback gets called. That's going to be our fire rate. And the final parameter is a Boolean, which will specify whether or not this timer should loop. Now, I would like our callback function called every 2 seconds, so I do want this timer to loop. So I'm going to say true. If we were to pass in false, then 2 seconds would pass, our function would be called, and that would be it. But since we set it to loop, our function will be called after 2 seconds, after which the timer will restart, and then after 2 more seconds, the function will be called again, and it will continue looping until the game is over. So we now have a function bound to our timer, and it's set to be called every 2 seconds. So we've bound a function to our timer, and it's going to be called every 2 seconds. But we'd like some sort of proof or confirmation that this function is actually being called. So for your challenge, in the tower class, go into our new callback function, check fire condition. Make sure the tank is in fire range. You're going to check the distance from the tower to the tank, and we know how to do this because we're already doing this in the tick function. So you may need to look in the tick function and see how this is done to remind yourself. Now check that distance, make sure we're in fire range, and then if we are, call the fire function. Pause the video and implement this now. Okay, so I'm back in tower.cpp, and I'm just going to scroll up to the tick function to remind myself how I got this distance and checked to see if it was in fire range. Now, we could simply reuse this code down here in check fire condition. Now, reusing code is not very efficient, so we may think about refactoring this, but first, let's just make sure we got this working. So we can first check our tank pointer to make sure it's valid. So I'm going to do that here in check fire condition. I'm going to say if tank, and if the tank is valid, the next thing we can do is get that distance, which is this value here calculated with the fvector dist function. So I'm going to take that and place it down here in check fire condition. Now the next thing we do is check to see if distance is less than or equal to fire range. So that's what we'll do down here. We'll say if distance is less than or equal to fire range. And if that's the case, then we can simply call the fire function. So we're going to call fire, and it's as simple as that. So let's go ahead and compile this, and we're back in the editor, and I'm going to hit play and get in fire range, and I can see that our towers are drawing debug spheres at the tip of the barrel. So we can see that that fire function is being called, and it works the same way for the tower as it does for the tank. So this is great. This is proving to us that our timer is running and our callback function is being called every 2 seconds. Okay, so we've got this fire function called every 2 seconds. Now in check fire condition, we have this functionality where we're seeing if we're in range, and we're doing the same exact thing here in the tick function. So this is a perfect opportunity to refactor. We could create some sort of function that will return us a boolean if we're in range with the tank. So why don't we go ahead and just quickly refactor this into a bool returning function. So here in tower.h, let's create a private function. It's going to return bool, and we're going to say in fire range. Now this is a simple game, and our tower is only going to be in range with the tank. So this is not ambiguous because there's nothing else that the tower would ever want to check to see if it's in range of. Now, if this were a more complicated game with other things that the tower would want to check the distance for, then we might name this a little bit differently, but we can just simply call this in fire range. And what I'm going to do is implement this here in tower. So let's go ahead and create the function body. We're going to need that a tower prefixing the function name. And what we're going to do here is basically this same distance check. So we're first going to check to make sure tank is valid with an if check. Now, if it is, then we can get this distance. So we can copy this line and just create our local distance float right here and simply check that distance against the fire range. So we can say if distance is less than or equal to fire range, and if that's the case, we can simply return true. This function can return the value true, and now we have a function we can call that will return true if we're in range. Now, as soon as we hit this return true line here in the if statement, then the function will return. We'll jump out of the function, so anything else after this if statement will not run. So what we can do is at the very end of our in fire range function, we can return false. Because if we ever reach the return true, we will never actually get to the return false line down here. We'll simply exit from the function early. But if we're not in range, if this distance check here fails, then we'll never hit the return true, and we'll reach the end of the function and return false. So this function will return true or false based on whether or not we're in range. And we can use this instead of using repeated code in our two functions. So up here in tick, for example, we only need a single check to see if we're in range before we rotate the turret. So what we can do is we can say if in fire range, and if this returns true, we are in fire range. So we can call rotate turret. So we'll put that right there in the if statement. And now all of this code is unnecessary. So we can simply delete it. And now this looks a lot cleaner than what we had before. And then we can come down here into check fire condition and do the same thing. Instead of all this, we can simply check if in fire range. And if we are, we can simply call fire. So now we've successfully refactored all of that code into a check that's made in our in fire range function. So let's go ahead and compile this again and just play test it real quick just to make sure that everything works as expected. So we're going to go ahead and hit play and get in fire range. And of course, we are in fire range and it's working correctly. So in summary, we created a timer, and every 2 seconds, we're calling the fire function in the tower class. Now, we're also checking to see if tank is in range, so we're only calling the fire function every 2 seconds if the tank is within the fire range distance. And we also saw that we were using that distance check in two different functions, so we refactored it into its own function, and we simply call that to check to see if we're in range. So we now have a fire function called on the tower class. The next thing to do is to actually start spawning projectiles with our fire function. So we're going to talk about that in the next video. I'll see you soon.
You probably know Vistaprint for business cards, but did you know we print everything you need to brand your business? We print banners and signs that help you stand out. And
now we're ready to
like
create
tote
a
bags,
projectile
t-shirts, and
class.
If you need
now our
we
tanks
print
and
it.
our
Put it all
towers
with 20%
need
off
to
for new
fire
customers with code
projectiles,
NEW20
which
at
means we're going to need
Vistaprint.ca.
a C++ class for the projectile. Now the projectile is going to need its own static mesh so that we can see the projectile once we spawn it in the world. So we're going to create the C++ class, and then we'll create a blueprint based on this class. And this is going to be a challenge for you since these are all things that you already know how to do. So you're going to create a new C++ class and choose the correct parent class. Now the projectile doesn't need to handle any user input, so that should tell you right there that this is not going to be a pawn. Now once you've done this, add a static mesh variable, just like we've done for our other classes. Construct it in the constructor using createDefaultSubObject and set the static mesh as the root component. Now, once you're done, go ahead and create a blueprint based on this projectile class. And in the blueprint, set the static mesh property for the static mesh component. Pause the video and create the projectile class now. Okay, so we're ready to create the projectile C++ class. So I'm going to go to File, New C++ class, and because we don't need user input, this is just going to be a basic actor. An actor can be placed in the world or spawned in the world, and we're going to be spawning these in the world, so we need to derive from the actor class. I'm going to click Next and name this new class. Now this is a projectile, so I think projectile is a perfect name for this. I'm going to leave it in the same folder as all our other C++ classes and click Create Class. So here we have projectile.h and projectile.cpp, and we need to add a static mesh variable. So I'm going to add a private section just under the protected one. So private, and we're going to need a uStaticMesh component. So this will be a uStaticMesh component. It's going to be a pointer. Now that's okay if you named it something different. I'm going to call this projectile mesh. Now we're going to expose this using uProperty. So uProperty, and I'd like to be able to edit this from the default blueprint. So I think edit defaults only is appropriate for this. I'm going to give it a category, and the category can be combat. It's not really important what we call it. And that's all the exposure I'm going to give this variable. That's okay if you have different uProperty settings here. Now we need to construct this, so let's go into projectile.cpp into the constructor and say projectile mesh. And we're going to call create default subobject using uStaticMeshComponent. And for the text, I'm just going to say projectile mesh. And finally, we need to set this to be the root component. So I'm going to say root component equals projectile mesh. And I'm going to spell it correctly there. Okay, so that takes care of the C++ side of things. Now, you may not have thought of this, but we have this primary actor tick, B can never tick equals true. And because our projectile doesn't really need to tick, we can set this to false. So if you'd like, go ahead and set that to false along with me here. And we do get the red squiggles here under the assignment operator. And this is simply because we need to include the header file for uStaticMeshComponent. So if we go to basepawn.cpp, we can see that header file here because we needed to include it for the static mesh components in the base pawn. So I'm going to steal that include and paste it right here at the top. And that way, uStaticMeshComponent is defined. Now let's go ahead and compile this. And I'm back here in the editor. And the next thing we need to do is create a blueprint based on projectile. Now I'm going to go into the blueprints folder, and we have a pawns folder. I'd like to create a new folder and call this actors, because our projectile is not a pawn, so it doesn't really need to go into the pawns folder. So we have a new actors folder. I'm going to go into it, and this time I can right click and select blueprint class. And here we can select the class to base this blueprint on. If we click the drop down next to all classes, then we can search for print class. And here with folder, I'm going to go into it, and this time I can right click and select blueprint class. And here we can select the class to base this blueprint on. If we click the drop down next to all classes, then we can search for projectile. And there is the projectile class. So I'm going to select that, click select, and now we have a new blueprint based on the projectile class. So that's another way to create a blueprint based on one of our C++ classes. Now I'm going to call this BP underscore projectile. And I'm going to double click to open up BP projectile. And I'll click open full blueprint editor. If you see that, go ahead and click on it. And we have our blueprint. And here's projectile mesh. And by default, it doesn't have its static mesh property set. So we're going to set that, and I'm going to choose the SM projectile. I'm sure that is what you selected for your projectile. Makes sense. So we have a projectile. Excellent. I'm going to compile and save. this, close out, and we now have a projectile, and gave it a U-static mesh to work with. We're ready. Hello and welcome back. Now we've already created our projectile class, and we're ready to start spawning these things in the level so that we can launch them at the towers and eventually destroy them. Now, spawning actors is going to involve the spawn actor function. So we're going to learn how that works in this video. Now, let's talk about spawning the projectile. This is something we'd like to do from the C++ side of things. We're going to call C++ functions to create new objects dynamically in the world. Now, we're spawning from the C++ side of things, but we'd like to spawn an object that contains additional information component. So we can't object in C++, which is based on a blueprint. Well, we're going to learn about something called class of requires. When I say variable, that type. So let's see how this T subclass of thing works. Are going to be spawning projectiles. So I'd like a T subclass of variable here. So I'm going to say T subclass of, and in the angle brackets we need to pass in a type. Now we can forward declare even inside angle brackets like this, and I'm going to make the type a projectile. And the reason is because we created the projectile class, and its type is a projectile. So I'm going to create this variable, and I'm going to call it projectile class. Now this is going to allow us to have a C++ variable that represents a class type, and the type can be based on a projectile, even a blueprint class type based on this. Now I'm going to give it a U property. And because I'd like to be able to edit this, at least in the default blueprint, I'm going to make this edit defaults only. Now we can give this a category. I'll place it in a category called combat. Now let's go ahead and compile this. Okay, so I'm back in the editor, and I'm going to go into the blueprints folder, and from there into the pawns folder, and I'm just going to open up BP Pawn Tank and open full blueprint editor. Now if I look in the details panel, I can look for combat. Here it is, and here's the projectile class variable. This is that T subclass of that we called projectile class. Now notice we can set it here, and we can set it using a drop-down. And if we click on the drop-down, we have three options. We can set it to none, which is what it's set to by default, which basically means it's a null pointer, or we can set it to projectile or BP projectile. That's what T subclass of allows us to do, is set this projectile class to a particular type based on projectile, since that's the type we chose when we made the variable. Now projectile here, this is the C++ class called projectile. In C++ it's a projectile, but BP projectile is a blueprint based on the C++ projectile class. And we can choose this, and now projectile class is set to the BP projectile type. Now this is not a component, and it's not a BP projectile object. It has built-in functionality that to the BP projectile blueprint type. Function belonging to the UWorld class. So if we get a hold of the world, we can call spawn actor. And spawn actor is another template function, and it's designed to create new objects, similar to create default subobject. But create default subobject is designed for creating components, and we can only use it in the constructor for a particular class. Spawn actor can be called at runtime while the game is running, and it can create actors. Now, it's a template, so it requires a type. If we're wanting to spawn a projectile, then we would pass in the C++ class type here, a projectile. This is the C++ class that gets returned by the spawn actor function in C++. Now, the parentheses take a number of parameters, including a uClass. Now, there are multiple overloads of this function that take different input parameters. The most simple, perhaps, is the version that takes a uClass, a location, and a rotation. The uClass is what represents the type to spawn. This is the actual type of the object that gets spawned. This could be a blueprint class. The location is an F vector specifying where to spawn the object, and the rotation will specify its rotation. So an example of the syntax looks like this. We would call spawn actor, specifying the class type, and then passing in that uClass information along with a location vector and rotation rotator. So let's talk about uClass for a second. Now, as we've been saying, uClass represents a class type. When we call spawn actor, we pass in a uClass to provide the spawn actor function with information about the object to spawn. Yes, we passed in a type in the angle brackets, but that simply tells spawn actor the C++ type to create, whereas uClass contains more information. Let's say we created a blueprint based on a projectile. And in the blueprint, we set some properties, such as choosing the static mesh for the static mesh component. Now, if we were to just spawn a raw C++ class, then that static mesh will not be set on the newly spawned projectile object. Essentially, we'd just be spawning an invisible new actor. However, a uClass variable can represent a blueprint class. uClass gives us the ability to have a variable on the C++ side which represents a blueprint class type, and spawn actor can take that uClass as an input argument so that it can spawn a new object based on the blueprint represented by that uClass. So a new projectile will have its static mesh property set because we're spawning a new object based on the blueprint and not equal to BP projectile from our BP pawn tank blueprint. So now you know how to words for this function. You pass in the C on the projectile, so don't function. You're gonna... Okay, so let's go and eat this function rotator called rotate. So next, I need to call... Now, I'm gonna remove draw debug. So now we have that type for that. So up here, I'm going to remove draw debug helpers.h. and replace it with projectile.h. So now we have that type included. Now, so we're going to pass in. And we're back here in the editor and we can test play. So I'm going to go ahead and click and check that out. We have spawned a new projectile. We're spawning the projectile at the tip of our barrel, and they kind of just hover there in the air, which doesn't really look right, but that's okay. This is step one. We first have to spawn the projectile. Getting it to act like a projectile is the next step. So in summary, we are now spawning projectiles. This is a great milestone. However, they're not quite projectiles yet. They just hover there, and projectiles are supposed to fly through the air. Actually launch through the air and behave as projectiles should. Hey, welcome back. To handle this, the update every frame is to simply add an impulse to the projectile and let the physics engine take over. Essentially, we're applying a force and launching that projectile and letting gravity do its thing, and the projectile will just fly off into the air. Now, another way would be to use a movement component. Now, this is a special type of component parameters. Now, it just so happens that Unreal Engine, so this takes advantage of some of the built-in and by class. And this is what will handle the component which belongs to the class speed, and the projectile movement component will act that we're concerned with. And you'll see that it says projectile movement component up move. The root could be set on the movement component, and take a look and see what the projectile move to this. So you expose this by making it visible anywhere, and that way we can easily edit the projectile movement component from within Blueprints. Now, you're going to construct it in the projectile constructor using create default subobject. Don't forget to include the proper header and set the initial speed and max speed variables of the projectile movement component. Now, choose your own values for these and set them in the constructor. Then playtest the game. You're going to adjust initial speed and max. speed in the Details panel by selecting the component in the projectile blueprint, and this will give you. I'm going to make this a private variable. Projectile. Now, I'm going to give it a category. If not, that's totally fine, but I'm going to. Now here in projectile.cpp, I'm going to include the header file. So back to the documentation page, I'm going to copy this include and simply paste it in here in projectile, and now I'm ready to construct my component. So I'm going to say projectile movement component, and I'm going to use create default subobject, and the type will be U projectile movement component. And for the text, I'm simply going to call this projectile movement component. Now, and I'm going to give, and through playtesting, we'll adjust this to the right value. Now, I'm going to set projectile move. So initial speed is going to be how fast the projectile component is when it starts, and of course, it'll never go over max speed. Let's go ahead and compile this. Okay, so I'm getting a compilation error, and if I go up, I'll see that it's referencing projectile.h. So let's go back to projectile.h, and it says projectile.h 27. It's referring to line 27, and that's this line right here. And we get this projectile movement component is not compile again, and we saw that this one is not. That projectile movement component, we have initial speed. I'm going to hit play and left click and check it out. Eventually what we'd like to do is have them blow up and cause damage, but this is a great starting point. If you're wondering why the turrets weren't actually spawning projectiles, you may not have set that. So let's go ahead and go into pawns. And BP pawn turret and open full blueprint editor, and we placed the projectile class in the combat section. This is our T subclass range. So let's take a look. Looking awesome. So we now have projectiles. So let's take these health, damage, and welcome back. Now in this video, we're going to talk about hit events. We would like to detect when the projectile hits something, and that way we can do something in response. events, such as destroy the projectile, and later we'll handle doing damage and New static mesh component is one class in a long hierarchy geometry, generally to be rendered or used as collision. Have uScene component, and derived from that, uPrimitive component. And you can keep scrolling down and see all of the other classes that derive from uPrimitive component. Now the reason we're pointing this out is because uStatic mesh component inherits the presented by the include so generate responds to that. Now being a static mesh component, it inherits things from component hit signature. And if we click on this, we see that F component hit signature is a struct. Now going back, we can see that the documentation says an event called when a component hits or is hit by something solid. This could happen due to things like character movement, using set location with sweep enabled, or physics simulation. For events when objects overlap, such as walking into a trigger, see the overlap event. So there are hit events and there are overlap events. We're concerned with hit events. So we know that onComponent hit is described in the documentation as a hit event. And we know that onComponent hit is a struct of type FComponent hit signature. So far, so good. Now this hit event, onComponent hit, is also something we refer to as a multicast delegate. A multicast delegate can have multiple functions bound to it. There can be functions that exist on multiple classes, and if those functions get bound to this multicast delegate, then they're added to something called an invocation list. This is a list of functions to be called when this hit event tells them all to be called. We say that this hit event or multicast delegate broadcasts when something happens. So in the event that our projectile mesh hits something, then the delegate will broadcast to all classes that have a function bound to this delegate. As soon as that broadcast is sent, then all of these bound functions are called and waits first. So we bind a function to this delegate, which we can use this for, and the callback function, which is the address of some function on our class. So once we access this onComponent hit delegate. Component hit event. So let's create a private themes descriptive primitive component pointer, and it's called hitComp. This is the component doing the hitting. In our case, we're going to have our projectile mesh hitting things. The next parameter is an actor pointer called otherActor. This is going to be the actor that got hit. The next input parameter is another primitive component pointer called otherComp. This is the other component that was hit. So if we hit the static mesh component of some other actor, then this would be that static mesh component. Next is an vector called normal impulse. If we're simulating physics, the physics engine will apply an impulse in response to the collision, and this vector represents the direction and the magnitude of that impulse. And finally, we have an input parameter of type const, fHitResult, and this is a const reference, and it's called hit. So when onHit gets called, we'll have access to a hit result that contains even more information about the hit. Now, since we're binding this to a delegate, it has to be a ufunction. So we're going to mark this with ufunction. Now, you should be familiar with ufunction. It's just like uProperty, only it's for functions rather than variables. So very important, our callback has to be a ufunction for this to work. Now, we've declared the function. Let's go ahead and define the function. So back in projectile.cpp, just under our tick function, let's define this function. We'll give it a function body and put the class name just before the function name. And now we have a callback function. So we're ready to bind this onHit function to our delegate, and we need to do this in begin play. Doing it in the constructor is too early, and sometimes you can run into issues like your delegate not being bound. So we're going to do it here in begin play. So we have our projectile mesh, and we'll use the arrow operator to access the variable inherited from uPrimitive component called onComponentHit. And onComponentHit has the function addDynamic. Now, strangely, autocomplete is not going to work for addDynamic, so you're going to have to type the entire function name. This is the function we'll use to bind our callback to onComponentHit and add that function to its invocation list. Now, first we need the user object. That's going to be this, because this is the class we're binding the function for. And next we need the address to the function. That's going to be the address of onHit. So we'll use the address of operator and the function aProjectile onHit. And with this, we have our function bound, and we're ready to generate hit events. Now we can test this out with a UE log, and we can use logtemp, warning, and for the text, we can simply say onHit. And if we see this in the output log, we know that our onHit function has been called. Let's compile this. So I have the output log open here. I'm going to press play and fire a projectile. And there's my log message. onHit is being called, so this is working. Now, just a side note, if we go into BP projectile and select projectile mesh, in the details panel, we can scroll down to the collision section, and here we see that the collision presets is set to block all dynamic, and that collision enabled is set to this setting, collision enabled query and physics. This is necessary for hit events. We need to be able to query for a hit event, and of course physics allows the physics engine to act on the projectile mesh. So now that we've bound to the onComponentHit delegate with our onHit function, and we've placed a UE log to make sure that it's working, I'd like you to explore this function a little bit more so that we can understand some of these input parameters in our onHit is set to this setting, collision enabled query and physics. This is necessary for hit events. We need to be able to query for a hit event, and of course physics allows the physics engine to act on the projectile mesh. So now that we've bound to the onComponentHit delegate with our onHit function, and we've placed a UE log to make sure that it's working, I'd like you to explore this function using the getName function s format specifier in the UE log text macro, and just as a reminder, actor just after on other tile mesh, calling get name, and that's because so this we have learned cast have this callback. Hey, welcome back. Now we have our event called a help. So let's discuss. It's more basic than the belongs to the actor component specifically. So select that, click next. Editor and make our new actor component class. So we'll go up to Tools and New C++. Class, and if I scroll down, I can see actor component. This is what we're going to select. Now be careful, don't select actor. That's a different class. It's actually a bigger class and has a lot more things than the actor component has. We need actor component specifically. So select that, click next, and this we can call simply health component. Let's click create class. Now here we have our new health component.h and .cpp files, and you can see here that uHealthComponent, the class we just created, is derived from uActorComponent. So make sure you have the correct type here, and you'll see that it has in its uClass macro this meta specifier, and it says blueprint spawnable component. This is what's going to allow us to add this component directly in blueprints, which is what we're going to do. Now the uHealth component is going to take care of health, which means we need a couple of variables. Let's go ahead and add these, and I'm going to make them private, so let's go ahead and add a private section just under the protected one, and we can add a couple of health variables. Now these are going to be floats, and I'm going to call the first one max health. This will be the maximum amount of health that we can have, and we can set this to a default value such as 100.f. Now, in addition to max health, we're going to have a health value, which will be the current health, and this will be what changes as we take damage. So let's make another float and simply call this one health. Now, we can initialize health to 0.f and then set its value in begin play. And the reason we'll do that is because max health is going to have its own U property, allowing us to set it from within the details panel. So let's give this a U property and make it edit anywhere. That way we can change it as we're developing. And then in healthComponent.cpp, here in begin play, we can simply set health equal to the value of max health. So that way, when the game starts, health will have the value of max health even after we've changed it in the details panel. Okay, so let's compile this. And back here in the editor, I'm going to open BP Pawn Tank and open the full blueprint editor. And now I can add this health component here in the components panel. So I'm going to click add and search for health, and here we see health. Now we called it health component in C++, and in fact the pop-up shows that it's called health component. So it strips away that component part when showing it here, and you may have noticed that when you look for static mesh components or capsule components, you don't see the word component here either for those. So click on health, and now we have our health component. And you'll see that under health component, we have max health and it's set to 100. And we don't see health because we didn't expose that variable. So now BP Pawn Tank has a health component, and it's said that the tank owns this health component. The BP Pawn Tank is the owner of this health component. Let's compile and save and close and open BP Pawn Turret and open the full blueprint editor, and we can add a health component to the pawn turret as well. So let's click add components, search for health, and select health, and now we have a health component on the tower as well. So I'm going to compile and save these, close out, and save all. So we now have a health component, and we mentioned that we'd like to have a health component so that we could reuse it with different classes. So if we have a pawn in the world, say our tower, it's going to have its own health component, and a hit over the example, which could get destroyed. Cast delegate just like on component any damage, the on take any delegate can broadcast and any functions that's getting damaged. So if we call apply damage, the actor's on take any damage delegate will be fired, and that callback function will be called in response. So apply damage is what generates the damage event. So to set all of this up, we have 3 steps. First, create a callback function, and since this will be bound to on take any damage, it must have the correct input parameters so that on take any damage will call it and pass in all of the associated information about the damage event. Step 2 is to bind this callback to the delegate. We've seen how to do this with the onComponent hit delegate using the add dynamic function. We'll be doing the same thing here. And the third step is to generate the damage event by calling the uGameplayStatics function applyDamage. So let's hop back into code and start setting this up. Okay, so we're here in health component and we're going to add a callback function. Now this can be void and we can call it anything we like. I'm going to call this damage taken, and because we're binding this to a delegate, it has to have the correct input parameters appropriate for that delegate. Now for functions bound to the on take any damage delegate, the input parameter list has to be as follows. The first is an A actor pointer called damaged actor. And this is what it sounds like. It's the actor taking the damage. Next is a float called damage, and this is the actual damage amount. Now next we have a const uDamage type pointer called damage type. And the reason we have this input parameter is because Unreal Engine has the concept of damage types. You can create custom damage types that have extra data that can inform you to do different things depending on the type of damage. You may have fire damage, poison damage, explosive damage, and so on. And if you want to implement custom functionality for each damage type, then you would implement that in your own custom damage type. Now, we're not creating our own custom damage type, but because we're binding this function to the onTakeAnyDamage delegate, it has to have these input parameters. So we're including it here. Now, the next parameter is an A controller pointer, and this is called instigator. In the Unreal Engine damage system, an instigator is the controller responsible for the damage. So if the damage was ultimately caused by a player controlling a pawn, then the instigator is the controller that's possessing that pawn. Now there doesn't always need to be an instigator. If there was none, then this would simply be null. And now I'm getting the red squigglies, so I can forward declare the A controller class here in the parentheses for the function. Now, the last parameter is an A actor pointer, and this one is called damage causer. This is the actual actor causing the damage. This would be the projectile itself. So we've declared this damage taken callback function, and just like our other callback function on hit, this has to be a U function. So we're going to give it the U function macro just to make sure that it works once we bind it to the onTakeAnyDamage delegate. And now that we've declared it, we're ready to define it in the .cpp file. So here in healthComponent.cpp, down at the bottom, I'm going to go ahead and give this a function body and fully qualify the function with the class name. And now we have a callback. So now we need to bind this to the delegate, but the delegate doesn't exist on the health component, it exists on actors. Specifically, we want to bind this to the onTakeAnyDamage delegate in the pawn that owns this component. So how do we access the owner of this component so we can bind to one of its delegates? Well, we would do this in begin play, and the way we can access the owner of a component is through the getOwner function. If you hover over this, you'll see that it returns an A actor pointer. This is the pointer to the actor that owns a component. Components can be owned by pawns, they can be owned by actors, so it will return the owner in the form of an actor pointer. So we have our callback function, and our second step is to bind it to the delegate onTakeAnyDamage that's going to exist on the pawn that owns the health component. So since you have experience binding callbacks to delegates, this will be your challenge. In the health component class, in begin play, you're going to bind damage taken to the onTakeAnyDamage delegate that exists on the owner of the component. So you're going to access that delegate through the getOwner function. In other words, you're going to call getOwner, and from that, you're going to access onTakeAnyDamage. And then from there, you know how to bind callbacks to delegates using addDynamic. If you get stuck, look at how we bound the onHit callback to the onComponentHit delegate. Pause the video and bind damage. Damage taken to the onTakeAnyDamage delegate now. Okay, so we're back here in health component and we're ready to do the binding of our callback. That's going to be this. Damage events. We created a callback damage taken. Hey, welcome back. Now we've set ourselves up with a callback function bound to the delegate onTakeAnyDamage. And the last step is to actually generate that damage event. And we want to do this when our projectile hits something. Once we broadcast for this delegate, we can apply damage to the thing that we hit. And we're going to broadcast this event using ApplyDamage, which belongs to the Gameplay Statics class. So let's take a look at the ApplyDamage function. Now here's the documentation for ApplyDamage. It says hurts the specified actor with generic damage. So this is a generic function for applying damage, and what we do in response to broadcasting for this delegate is up to us. Now here we see we need to include gameplay statics, and in the syntax we see several input parameters. Now we actually get some description of the parameters if we keep scrolling down. We see that damaged actor is, well, the actor that will be damaged. Base damage is the base damage to apply. Really descriptive documentation here. Thanks, Epic. Event instigator is the controller that was responsible for causing this damage. And it says, for instance, the player who shot the weapon. When it says player, it's referring to that controller. Then we have the damage causer, which is the actor that actually caused the damage. It says the grenade that exploded. In our case, it'll be the projectile that exploded. And finally, we have damage type class, which is a class that describes the damage that was done. Now back up in the syntax section, we can see the types of these inputs, and we see that damage type class is a T subclass of, and we've seen before that T subclass of will satisfy an input parameter of type U class. Well, when we call ApplyDamage, we can pass in a U class representing the damage type we'd like to use. So we'll talk about how we're going to satisfy this input parameter in the projectile.cp_in once it gets called. When the onComponent hit parameter, it's going to be variable, and we can initialize it to a value, let's say something like 50.f. And since this is something we'd probably want to experiment with, we can give this a U property to expose it and make it edit anywhere. So now we have a damage amount to pass in when we call takeDamage. Now the next parameter is the instigator, and we saw that this is of type a controller. So how are we going to get the controller? Well, we've seen that we can get the owner of a particular component with the getOwner function, and this returns the actor that owns a particular component. These projectiles are being spawned dynamically, so we need to make sure if we're going to be calling getOwner that the owner is set. Now we're spawning these from basepawn, so if we go into basepawn.cpp, here's the line where we're spawning the actor. But spawnActor also returns a pointer to the actor that was spawned. So we could store this in a local variable. For example, we could say auto projectile and assign the value returned from spawnActor. Now, if you're not familiar with auto, it allows the compiler to figure out the type to assign to this new variable. If you hover over it, you'll see that it has the type a projectile pointer because that is what we're assigning from the spawnActor function. So this is the same as if we had put a projectile pointer right here. And now we can access that newly spawned projectile. And the reason we want to do that is we'd like to set its owner. We would like to make sure that its owner is set to the pawn that spawned it. So we can say projectile, and there's a function for this called setOwner. SetOwner takes an actor, and we're going to pass in this so that whenever one of our pawns spawns a projectile, it will set that projectile's owner, so that way if we ever call getOwner further down the line, we'll get the instance of the class that owns that projectile. So back here in projectile.cpp, we have our getOwner function call, and we can store this in a local variable. I'm going to go ahead and use auto again and call this myOwner and set it to the result returned by getOwner. So now we have a local actor pointer that stores the value of the owner. Now we can access the instigator controller from this actor. Now before we do so, it's a good idea to check to make sure myOwner isn't null. So I'm going to say if myOwner is null equals null pointer, then I'm simply going to return. Now if your if body has a single statement like this, you can place it on the same line without the curly braces, in case you didn't know. And null pointer is a keyword in C++ that allows you to check to see if a pointer is a null pointer. So if myOwner is null, then we will return out of the function early and not do anything else. Now, as I was saying, we can get the instigator controller from myOwner, and that's with the use of the function called getInstigatorController. And if we hover over this, we'll see that it returns an A controller pointer. I'm simply going to use auto and store this in a local variable that I'll call myOwnerInstigator. So now we know what to pass in as the instigator. The next input is the damage causer, and this is the actor doing the damage. For the projectile, this is going to simply store this in a local variable that I'll call myOwnerInstigator. So now we know what to pass in the damage. For the projectile, this is going to simply be this. And that leaves the last input parameter, which is a damage type. And we saw that it's a T subclass of, which means we need the proper U class to pass in. Now here's the Unreal Engine documentation for U damage type. It says a damage type is intended to define and describe a particular form of damage and to provide an avenue for customizing responses to damage from various sources. Now, we're not going to customize our damage, we just need to satisfy the input parameter, which means we need a U class value that represents this U damage type class. Now, in C++, if we want to get the U class of any particular class, such as U damage type, we can call a function called static class. This is inherited from the UObject class. Now, of course, we're using U damage type here, so we'll need that header. So From the documentation, I will copy the include line and I'll paste it up here at the top of projectile.cpp. And now you'll see that this static class function returns a uClass pointer, and that uClass will represent the uDamageType C++ class. Now, since we're not creating a blueprint based on uDamageType and setting some extra data, we don't really need a T subclass of variable. So in this case, we can use static class, and this will return a uClass that represents this type. And we can store this in a variable if we like, and I'll call this DamageType class. And this is what we can pass in as the final parameter to apply damage. So we now have all of the information we need to pass into the apply damage function. But before we do so, I'd like to place a couple of checks to make sure it's appropriate that we call this function. So I'll make an if statement here. First, I want to make sure that other actor is not null, so I'm going to place other actor here. I'm going to place an and here so I can check to make sure other actor is not equal to this actor. We don't want to cause damage to ourselves if we are the projectile. Now I'm going to place another and make sure that other actor is not equal to my owner. It wouldn't be good if the projectile is causing damage to its owner. And now if we get inside this if statement, then we know that it's appropriate to call apply damage, so we can do so. And that's going to be your challenge. So in our new if statement, in actor, we don't want to cause damage to ourselves if we are the projectile. Now I'm going to place another and make sure that other actor is not equal to my owner. It wouldn't be good if the projectile is causing damage to its owner. And now if we get inside this if statement, then we know that it's appropriate to call apply damage, so we can do so. And that's going to be your challenge. So in our new if statement, in the onHit function, call the uGameplayStatics apply damage function. This means you'll need to include damage in the onHit function now. Okay, so I'm here in projectile.cpp and I'm going to include the header file for gameplay statics. And we can see from the apply damage documentation page that the include is kismet/gameplaystatics.8. I'm going to call uGameplayStatics apply damage. Now, as soon as I type that opening parentheses, I get the pop-up reminding me of the input parameters I need. And the first one is the damaged actor, and that's going to be other actor. So we're going to type other actor. Next, we need the damage amount, and we added this damage cause. We're now called to do something here in damage taken. Well, it would make sense to take this damage and subtract that amount from the health. Before we do that, though, I'd like to make sure that damage is not less than or equal to 0.f. It makes sense to make these checks before decrementing damage, just to make sure that we don't apply a value that doesn't make any sense, like 0 or a negative value. So if that's the case, we'll simply return. And of course, if you'd like to be slick and do what I did in projectile.cpp, we can place the return right there. Now, if we make it past this line, damage is a positive value, so we can take health and use minus equals damage. And just to make sure that this is working, why don't we place a UE log here? So UE log temp warning text, and we can simply print the value of health with %f and health. And with that, we can compile. Now, with a successful compile, we'll hop back into the editor, and with our output log open, let's hit play. Now, let's see if we can get hit by a projectile. And there we go. Our health is now down to 50, and if we get hit again, We got quite a few hit events because we were hitting up against the projectile many times very quickly, but we see that our health is decrementing properly. So we do need to make sure we implement the correct behavior upon death when health reaches 0, but we also need to make sure that we don't get this hit event spammed. To prevent what we'll do in this video is have the projectile destroy itself, and that couldn't be easier. We simply call the destroy function. So with one more compile, back here in the editor, we can go ahead and get hit by a projectile. And look at that, the projectile is gone. So it does its damage and then it disappears. And of course, we can test out hitting the towers as well by blasting them with projectiles and making sure that those hit events are triggering. And as you can see, I can spam this with a whole bunch of projectiles, and we'll see that the health value for this poor tower here is getting very, very negative. So in summary, we called the apply damage function, and this resulted in a broadcast for the on take any damage delegate. We decremented the health in the health component, and we destroyed the projectile. So we've now taken care of damage. We have not yet taken care of death, so that will be one of the next things we'll cover in a future video. I'll see you soon.